Okay, so this is number 5.21 on the review. So this reads the CDF. Again, I shortened it a little bit, but the cumulative density function of a random variable x, which represents the time in years from the time a machine is serviced until it breaks down, is as follows. So capital F of x is equal to 1 minus e to the minus 4x, where x is greater than 0, and presumably it's going to be 0 otherwise. And then we want to find the mean time until the machine breaks down after service. So we want to find the mean, so we want to find the expected value of x, right? This is the mean, which is going to be equal to the integral from negative infinity to infinity of our density function f of x dx. But wait, we don't actually have our density function, we have our CDF. So how do we find this? Our density function, if we have our CDF, this is going to be the derivative with respect to x of our density function, of our cumulative density function. Because remember, to get this, what do? We integrated from negative infinity to x, right? To get the CDF. So, but yeah, so we really want to take the derivative of this here. So this is going to be equal to the derivative with respect to x of 1 minus e to the minus 4x. So derivative of 1 is going to be 0. The derivative of this, we're going to have minus, right? So derivative of e to something is just e to something. So we leave it alone at first, e to the minus 4x. But because this is not just x up here, we have to use, by the chain rule, we have to multiply by the derivative of this inside. So to multiply by the derivative inside is going to be what? Negative 4. So we have that the CDF is going to be equal to 4 e to the minus 4x. So from both of these statements, we could recognize this distribution. I think they're intending you to not do that, right? Because, presumably we haven't actually covered this is going to be an exponential random variable, and we haven't covered that yet, in this section. But since we have covered that, and this is a review, we could just use the fact that this is an exponential random variable, right? So for an exponential random variable, with parameter theta, right? Let's say y is exponential with parameter theta, then the expected value of y is going to be equal to just theta. And then what is our f of y? That's going to be given by 1 over theta times e to the minus y over theta. So if we compare these two, our theta, if we look at it for a second, our theta is going to have to be a fourth, right? We're basically setting 1 over theta equal to 4. And then it's going to mean that our theta has to be 1/4. So using that information, we could just conclude that the mean expected value of x is equal to a fourth. But let's also just do it the way that the problem probably intended us to. So we integrated, we got, we took the derivative of the CDF and we got our PDF. So now we want to integrate. So in our case, remember, this is going to be for x values greater than 0 because it's coming from this, right? So in our case, the only non-zero values for our PDF are going to be for x values greater than 0. So we're going to be integrating from 0 to infinity. Sorry, this should be an x here. I don't know why. I forgot that. But anyways, so this is going to be the integral from 0 to infinity now, x. And then our PDF is going to be 4e to the minus 4x dx. and this is going to be, we're going to have to use integration by parts, which I'm just realizing. Do I really want to do that? Sure, I will. That's fine. Yeah, okay. So again, remember when we're doing integration by parts, the way that I said to remember it is using the product rule. So if I take the product of two functions, that's going to be the derivative of the first times the second plus the first times the derivative of the second. I move one of these over to the other side. So I'll get f prime g is equal to fg prime minus fg prime. Now if I integrate both sides, this is f prime g. This is kind of sloppy notation, but that's okay. So then I'm integrating the derivative. In general, we have to be careful about evaluating, especially when we're looking at this. But anyways, this is going to be fg minus the integral of fg prime. So looking at this is kind of my integration by parts business right here. So what do I want to do? I want to say which one's going to be my f, which one's going to be my g. So the g, I want to set it so that when I take the derivative, it makes it simpler. So I really want my g, in this case, to be equal to x. And I really want my f prime. I'm going to change pens here. So that one's a little spotty at the moment. So I apologize for that. And I want my f prime to be equal to 4e to the minus 4x. So what does that mean? That means my g prime is going to be equal to 1. And that means my f, I kind of integrate this-ish, is going to be equal to minus e to the minus 4x. So let's check that. I take the derivative, it stays the same. I have to multiply by minus 4. I get back there. So that's good. So now what do we have? We have that this is going to be equal to, right, so we're going to have to do something first. So this is going to be equal to the limit as a goes to infinity of the integral from 0 to a, right, of x times 4e to the minus 4x dx. So now we can use this integration by parts technique. So this is going to be equal to the limit as a goes to infinity. So now this is going to become what? It's going to become f times g. So this is x times minus e to the minus 4x. And then I want to have this evaluated from 0 to a. And then this is going to be minus the integral of f times g prime. So g prime is just 1, so this is going to be the integral of minus e to the minus 4x. Again, from 0 to a dx. Right, so my room is kind of getting a little cramped here. So let's do like this. Maybe do something like this. Alright, so this is going to be equal to the limit as a goes to infinity. So I want to plug in a. So what do I have? This is, because I have this minus sign here, so this is minus a times e to the minus 4a. And then I'm subtracting off plugging in 0, but because of this x, that's just going to be 0. So yes. And then I'm going to have minus, alright, let's make this a plus because I have the two minuses here. And then I'm integrating this, so I can leave this the same. And then I have to note when I take the derivative of this, I want to cancel out to get back here. So I need to add something. So when I take the derivative of this, I bring, it stays the same, and I multiply by the derivative inside, which is minus 4. So to cancel that out, I need a minus 1/4 here. Right, so I take the derivative, that cancels out, I get back to here. And then I want to evaluate this from 0 to a. So let's bring us down here. So this is going to be equal to the limit as a goes to infinity of a, so minus a times e to the minus 4a. And then I'm going to have minus 1/4. And then, so I want to plug in a, so this is e to the minus 4a. And then plug in 0. E to the 0 is going to be 1. So I guess I'll just do it. So this is minus e to the 0. This is going to be 1. So what are we going to have? We're going to have that this is the limit as a goes to infinity of minus a times e to the minus 4a. So this is minus 1/4 e to the minus 4a, and then this is going to be plus 1/4. Right, so now to evaluate this limit, the limit of this term is definitely going to go to 0, right? The limit of this term, right, because we're basically going to have what? We're going to have a L'Hopital's rule situation. So we can do that. Why not? Let's do it. So let's calculate this on the side. So we want to calculate the limit as a goes to infinity of minus a times e to the minus 4a. So this is going to be equal to the limit as a goes to infinity of minus a over e to the 4a. So now this is going to be infinity over minus infinity as a goes to infinity. So we can, by L'Hopital's rule, set this equal to the limit as a goes to infinity of the derivative of the top, which is minus 1, over the derivative of the bottom, which is going to be, we leave it the same, e to the 4a, times the derivative of this exponent by the chain rule, so it's going to be times 4. And now, as a goes to infinity, this is going to go to infinity, so this whole thing is going to go to 0. So now we have that this goes to 0, this goes to 0. So 0 plus 0 plus 1/4. So our answer is 1/4. So again, we could go through this whole process to get 1/4, or we could recognize that this is an exponential distribution with parameter theta equal to 1/4. So either way,